We're in section 9.2, power supply applications, and the reason we're looking at power supplies is because they are a major use of diodes. Nearly all computers have some sort of power supplies. Now, a power supply circuit must do several things. One of them is to convert AC line voltage into a DC voltage required by the circuit. They also must reduce the AC voltage to a lower value, and they must continuously adjust the DC output voltage to keep it constant under varying load conditions. So first of all, this point here, we start out from the wall. We have an AC signal coming out of the wall. It is 120 volts RMS. And if we looked at it on an oscilloscope, we would see from here to here we have 170 volts peak. Now, what we want for a computer circuit is we're going to want about 12 volts DC, 5 volts DC, maybe 3.3 volts DC, a few miscellaneous values here. But this is a far cry from this. And so we're going to be using our power supply to do this. And so we're going to have a couple aspects here. We're going to use a transformer to reduce the AC to a lower value, and then we're going to use a rectifier to convert the AC into DC. And we start out with a half-wave rectifier. This is the most basic of rectifiers. The term rectify is used to describe the conversion of AC into DC. In a circuit shown, only one half of the input waveform is allowed to pass through to the output, and this is called half-wave rectification. So we start out with an applied AC voltage, and this will be the case with all of the rectifiers. We start out with an AC input, and we start out with a 10-volt peak signal. And so if we were to draw this kind of like this, from here to here on an oscilloscope, we would measure 10 volts peak. And notice that we have our diode in the circuit, and what is going to happen is we're showing the current flow is moving in this direction, and the reason we're showing it that way is because we have a positive value here, and we're showing ground here. And so the flow of current will be from the negative, or from ground to the more positive value, which is right here. And so that will forward bias our diode. Remember, our diodes, if we go from cathode to anode, the polarity needs to be a negative to a more positive, at least 0.7 volts worth, and that will cause this diode to conduct, and it will pass this signal. And so we will have this AC signal passed over. All of it except for the 0.7 volts will be passed to the output. Now, another way to view this, and I'm going to use this throughout this presentation, is to simply draw a battery over here. I'm going to put a battery with the positive on top and negative on the bottom, because at this point, when we're looking at this phase of the sine wave input, we're on the positive cycle. So you could put a battery in here, and this sometimes makes it easier to analyze a circuit of this nature, because it's very clear now that we're going from a negative to a more positive, and that will forward bias this diode. Okay, so we've looked at the positive half of this cycle, and we've seen that turned the diode on. Now, when we look at the negative half of the cycle, so we're coming in here, we looked at this, now we're looking at the negative half. Now, on the negative half, you're going to note the polarity of this diode. Remember, it has to be negative to positive. On this side, now we have a very negative value. Now, we could say we're going from ground to a more negative, but if we put that battery back in the circuit, it kind of makes a little more sense. If we except that we turn the polarity upside down here, if we go like this, and we connect the battery like this, it makes a little more sense, because now it's very obvious that there's a plus here and a negative here. And so this battery, or this diode, remember that you have all the electrons over here on the cathode. they're going to be attracted to the positive terminal here, and this will cause the depletion region to become very wide, and effectively this will be an open circuit, and there'll be no current flow here, and so there is no output. So the end result is that we have a AC signal coming in, and the output, we get half of it, and then it cuts off. And if we continued on here, you'd have something that looks kind of like this. And this is what we talked about, half-wave rectification. Okay, this is a description of what we just looked at. During the positive alteration, the diode is forward biased and the full applied voltage is dropped across the load resistor. During the negative alteration, the diode is reverse biased and acts like an open circuit. No voltage is present across the load resistor. The output voltage is actually pulsating DC. Looks kind of like this. An application for a half-wave rectifier is shown on the following slide. And so this is from your text. This is a circuit that would recharge batteries. Now this is a very basic one, and it utilizes a half-wave rectifier. So let's look at what we have here. First of all, we have 120 volts AC applied. We have a switch and a fuse. This goes into a 12-to-1 transformer from primary to secondary, and so the value that's going to be fed to our rectifier, let's take a look. We have 120 volts in, 12-to-1, we're going to divide that by 12, so we'll have 10 volts RMS. Now if we were to convert that to peak, remember our formula, if we took 0.707, 10 volts RMS divided by 0.707 is going to yield 14.1 volts peak. And so here we have this value here. Now this is one of the purposes that we mentioned in this lesson, was that the purpose of a power supply is to step down the high-end line voltage to a much lower value. So we use the transformer to step this down, and now we have about 14.1 volts peak applied to this diode. Now, remember that in a half-wave rectifier, our output looked kind of like this. We had the humps, and we called this pulsating DC. Now, that doesn't really look like DC, and the reason they call it pulsating DC is because it is all going positive, and if we were to average this value, we have an average DC level. And there actually is a formula for doing this. Your text doesn't address it. I'm going to mention it briefly. You're not going to be tested on it, but just for purposes of information, this is the formula. You take voltage peak divided by pi, or 0.318 times the peak voltage, and so in this case it would be 0.318 times 14.1, or 14.1 divided by pi. At any rate, it's going to yield a value about 4.5 volts DC, and that would be the average level delivered to this rechargeable cell over here. Okay, full wave rectifier. A full wave rectifier applies both halves of an AC waveform to the output. The circuit shown is called sometimes they're called a biphase half-wave rectifier. Sometimes they're called a center-tapped rectifier circuit. At any rate, they employ full-wave rectification. The operation of a full-wave rectifier is demonstrated in the figure shown on the following slide. And so here we have a full-wave rectifier. And when we say full wave, why don't I first describe what does that mean? Well, here we had an input wave coming in, and this is the positive, this is the negative. Now with a full wave rectifier, the thing that we're going to get as an output is something that's going to look kind of like this. So that we're going to be utilizing both the positive and the negative side of the input waveform, unlike the half wave that was only able to use half of it. Now, we probably ought to talk about this thing called a center tap. Now, we've alluded to these in our section about transformers, but let's quickly review. Notice the secondary here is split by a ground, and so this is going to effectively, whatever the voltage is in the secondary is going to be cut in half. Now, this is one of the inherent disadvantages of a full wave rectifier, by the way, but we're going to be looking at it. Okay. One way to view these circuits is to, you'll notice the polarity that's set up by this ground in this place. Notice there's a positive, negative, positive, negative. Sometimes it's helpful to draw the battery in here. And so notice the positive. Let's put a DC battery here and then another DC battery here. And notice that the ground is connected to this side and then to this side here. And we have a positive going directly to this diode and a negative going directly to this diode. Now, you know, a transformer does not represent two DC sources, but sometimes it's easier to understand the current flow if we look at it in terms of the batteries. What we actually have is here we have our input waveform coming in, positive to negative, and sometimes it's helpful to view this. Remember that on this one, actually this waveform is reversed, and so instead of going positive first, notice it is negative, and so on this side we could view the signal as going like this, because here it's positive and here it is negative. So the idea of this type of a device is that one diode will be on and the other will be off. And if we look at the polarities of our battery, it will make this the current quite easy to understand. Here, the upper diode is going to be the conducting diode, and you notice, remember that our polarity needs to be negative to positive across the diode in order for it to conduct from the cathode to anode. And you notice you have the large positive signal here, which would indicate this is probably going to be conducting. And notice on the bottom side, you have the large negative, probably tells, well, this is probably going to be cut off. But let's look at it in terms of the battery. Notice this diode. If we start, remember, the current flows from negative to more positive. So let's look at the path. It would go negative from the ground to the ground, and then it would go to the positive terminal. So effectively this diode sees negative to a more positive, so this diode would be conducting. This one would see just the opposite. It would have the negative on this side. Notice the negative polarity here, and the path for current coming up through here to the positive side, and so this would cut this diode off. Now, that is on the positive alteration. On the negative alteration, just the exact opposite happens. We could flip this battery over, and let's see if we draw it like this. And so we go like this, and then we connect ground, and then like so. And so now we are on, let's see, the negative. Let's see if we draw the sine wave like this. And then there's the positive and going like so. And again, now things are reversed. Now on the positive is here. In fact, if we look at the battery, if we go from negative to ground, from negative to the positive side of this terminal, this diode will be off. And if we look at this one, now this one, we've got the negative side of the battery here. And if we go through, the positive is here, and so this one will be cut off. Well, what's the end result? Okay, on this one, we had the positive cycle coming forward bias, this diode on the positive cycle, and then on the negative part of the cycle, the lower was forward biased, and so we had another half wave. And so this is constantly switching on every wave. The diodes switch. If it's 60 cycles, it's switching 60 times a second, and our end result is that we have an output that looks kind of like this. It's pulsating DC, but now we have twice as many pulses as we did before. In fact, if we wanted to backtrack this a bit, remember we said we had 0.318. Well, we're going to have twice that value with our full wave rectification. Okay, bridge rectifier. A bridge rectifier is more widely used than a center tapped rectifier. Circuit operation is best understood by examining the current paths of the forward and reverse bias diodes during each half cycle of the input waveform. Again, we have the input AC coming in, and we're going to, in this case, the value of the full wave is that you don't have to have the center tap transformer. You can just put the entire secondary across this device. Now, and so you'll be able to utilize the full secondary rather than just half of it. And it's going to utilize 2 diodes vice 1. Now, there's a minor disadvantage here in that since you're going through 2 diodes, instead of dropping 0.7, you drop 1.4 volts, but that's kind of a small consequence of being able to use the entire secondary of the transformer. But again, let's evaluate the paths for current and the respective diodes. So we have the AC signal coming. If we draw the battery here, let's see what we have. Again, in respect to the voltage source, let's look at the diodes. So here we have negative, and we're going to go here from negative to, and we're headed towards the more positive, and so from negative to a more positive, and so this is going to conduct. So we'd be one negative on this side, negative on this side, but the more positive on this side. So these two would conduct. Now, on the other hand, let's look at these 2 diodes. This has the positive is placed right here. This one, let's see, effectively the positive is only a 0.7 volt drop away, and the negative is right here. So these 2 diodes will be reverse biased, and these 2 will conduct. Now that's going to be on the positive part of the waveform, so we would have this resultant output on the pod. Now on the negative side, again, if we draw the battery kind of like this, and we take a look at this, on the negative side, again, if we look at the battery, at the diodes in relation to the battery, if we go from the negative terminal through the diode, negative to a more positive, with a negative there, and then up through ground, and again, we're going negative to the more positive terminal. These 2 diodes are forward biased. And again, the negative is connected here, and effectively the positive is connected here. And in this case, again, the positive is here, and we're going to have a negative value here. And so these 2 are cut off. So on the negative cycle, we will get another output. Now, for practical purposes, we come in with an AC signal, and we're going to get basically the same pattern that we had with the full wave, except that we're going to get a greater amplitude. And so these are more widely used than the center tapped variety. Most electronic applications require smooth DC current to operate properly. Filtering pulsating DC circuits accomplishes this. Adding a capacitor to the output of a half-wave rectifier filters the pulsating DC into smooth DC. Now, what will happen is in the notice we had, this is basically the rectifier. Remember, we had an AC signal coming in, and then our output looked kind of like this. And then now we have added a capacitor, and the capacitor is adding what we're calling filtering. Now remember, the nature of a capacitor is it charges to a given voltage, and then it will hold that charge for a period of time. Now in this case, I'm going to draw a little bit bigger picture of it down here. In this case, what is going to happen is that peak value is going to come in right here, and it's going to charge this capacitor, and it'll charge to the peak value, and then the capacitor will begin to discharge, and it will begin to discharge until again another peak value comes in and recharges it. And so it recharges to the peak, and then it begins to discharge, and then another peak comes in, charges it, and so you end up with a output that looks kind of like in this drawn right here. And so the original signal would look kind of like this, and like this, and like this, and like this, but the resultant is something that looks kind of like this, and that is the value you're seeing here is a bit exaggerated. Actually, it can get quite smooth depending on the size of the capacitor, and some circuits will utilize several capacitors. But this resultant value, this value, you see that this changing slightly, is referred to as the ripple. Okay, full wave rectifier with a filter. A capacitive filter added to the output of a full wave rectifier is shown at the right. One drawback of a half wave rectifier is the higher level of ripple voltage after filtering. Full wave rectification reduces this voltage. Now, so what you'll have with a full wave rectifier, remember that our output is going to look here. I'll draw here. Remember, with full wave output, we don't have half wave, we just had 1 and then 1 and then 1. And with half wave, or with a full wave, there is less time for this capacitor to discharge. Remember, in a half wave, we charged to the peak value, and then it had this much time to discharge. Now, in a full wave or a bridge, the time to discharge is half of that. So what you end up with is a more pure final output. Okay, other types of filtering. Simple capacitor filters is adequate for many electronic applications. In more critical applications, more complex filter networks are required to reduce or to eliminate the ripple. There are a couple here that your text refers to. One is the L filter, and another is the pi filter. We might show the L is simply an inductor, and then there is a capacitor, and the pi looks like a capacitor and with an inductor and then a capacitor, and I guess this looks like an upside down L, and this kind of resembles pi, I guess, anyway. But those are a couple other filters. We will not go into those, but simply to mention them. Okay, we've been looking at power supplies. We finished up looking at filtering, and this is what ultimately makes our DC output. Because remember, we talked about our purpose was we started out with a AC signal, and the desired result out was a smooth DC. And we mentioned computers need 12 volts and maybe 5 volts, and we want a smooth DC. Now, what we show here is that the DC might have little ripples in it, but modern power supplies have got some advanced circuitry that will virtually eliminate those ripples. So this gives us a methodology to take our 120 volts AC in and rectify it, transform it, and make it into a low-level DC suitable for applications like computers. Okay, there's the filters. We looked at bridge rectifiers. We looked at a full-wave rectifier. We looked at an application with a half-wave rectifier and half-wave rectification.